Swish! Hi guys, welcome back to Rationalix, and this will be a very strange Wednesday. Why strange? Well, because the first thing is that this video is in English, and the second thing, which is the most important one, is that because I will not be the only one person in this video, but I will share the stage with the one and only Gabriele Di Maggio. And for the people who don't know who Gabriele is, he's 13, I think, years old, and he's very talented. He has a great passion for mathematics and physics, and well, check out his channel on the description. So, in the first part of the video, I will solve question B1 from Putnam Competition of 2020. So, I will leave for you the exercise test on the screen, so you can check it. And, well, in the second part will be Gabriele's turn, but without losing any time, let's start with the B1 question. Let's check it. So, for the B1 question, we have our function. Let me write in the top of the board. So, we have dn, which is the sum of digits when n is written in base 2. So the sum of the digits of n in its binary expression. So when n is in base 2. So let me give you a first example of this function. So we have d of 13, for example, which is d of 1, 1, 0, 1 in base 2. And this will be the sum of the ones in this expression. So it is 1 plus 1 plus 1, which is equal to 3. So d of 13 is exactly 3. Now, the B1 question is asking us to compute this particular summation. So we have the sum from k equals to 1 to 2020 of minus 1 of dk times k to the third power. So, and this we want to compute it essentially modulo 2020. So, what is it, this modulo 2020? Well, this will be the goal of the exercise. So, let's start. Let me erase this part. Okay. So, in order to compute this particular expression, let me start with this identity. So we have 1 minus x, 1 minus x to the square, up to 1 minus x to the 1024. This, if you see, is a particular way to express this polynomial, which is k from 0 to 2047, let me explain why 47, of minus 1 to the dk x to the k. Well, why we have 2047? Well, because the biggest power which x appears in this particular polynomial expression is exactly 1 plus 2 plus 1024. So we have 1 plus 2 plus up to 1024, and this is very well known, is exactly the next power of 2, so 2048 minus 1. So this is exactly 2047. Now, why this equality holds? Well, if we take a particular x to the k, okay, now let us write k in base 2. So k in base 2, let us write as a0 plus ai times 2 to the I. Well, I is suitable, choose the in this expression. So x to the k, if you see, is exactly composed by minus x to the a0 times minus x to the a1, minus x to the ai. Well, if and only if all of these a0, ai are strictly bigger than 0. But this is an expression of k in base 2, so these ai are exactly 1. So in this way, the coefficient of x to the k is exactly minus 1 times what? Times the sum of the non-zero entry of the expression of k in base 2. So this is exactly dk, xk. And this gives this particular identity. Now that we have this particular identity, let us play with another identity which is very similar. So let us take 1 minus x up to 1 minus x to the 16th power. So as before, we can play exactly the same game, and in this case we have exactly k from 0 now to the next power of 2, so 32 minus 1, 31, and here we have exactly the same coefficients. Now we want to multiply these in order to reach 2047 from 31. Why this? Well, because many of the terms will cancel out in the future, in the very next future. So let us multiply all of these with x to the 2016. So here we have 2047 now, and here we start with 2016. Okay, but now we want to compute a sort of a term like this from a polynomial, in essentially of these forms. So how to do it? Well, if you look very deeply, you can check that if we multiply with x and differentiate first with x from the both sides of the equation, so let me use maybe a different bracket. So let us do the same thing here. What we have here? Well, in this case, by the chain rule, exactly you can do it, for example, as many times as you want, and you will always have a term like 1 minus x to the sum power in any summons of the expression of these types of derivatives. In this case, when I take the differentiation with respect to x and multiply with x, the only thing that changes is that it will appear a k as a coefficient for x to the k. So if we do it 3 times, here we have k to the 3rd power, and here we have a very bad stuff, but each of these terms will contain at least one term of the form 1 minus x to something. If we compute it at x equals 1, so if we substitute x equals 1, this will be 0. Why? Well, because there is, again, a single term of this form in any of the factors. And this, if we substitute x equals 1, will be exactly this type of formula, which is exactly a type of formula of this type. So we can do the same game in this expression. So if we play exactly the same game, here will be 0. Okay, now we have these two types of identities, and we can subtract, for example, the second from the first. So we have 1 minus 2, let me write here, and this will be the summation of k from 2015 this time, moreover, summation of k from 0 to 2015 of minus 1 to the dk times x to the k equals 0. Now, this is pretty similar to this, but here we have 2015 and here we have 2020. So, we are only interested in evaluating this particular sum only for the terms which starts from 2016 and ends up to 2020. So let me erase finally this part of the board. And now we have that our S, let me call it S, is exactly what? Is exactly minus 1 to the D of 2016 times, in this case, well, this is exactly k to the cube of 2016 cube up to the term of k with k equals 2019, because 2020 is already 0 modulo 2020. So we end up to minus 1 d of 2090 times 2019 cube. But this we can compute, for example, noting that 2016 is minus 4 modulo 2020. This is exactly minus 1. We can compute explicitly for the fourth number the value of d, and this you will check it by a very simple computation. I have already the result written here, is exactly 1990 modulo 2020. And this is the answer to the B1 question from Putnam. Okay guys, my job here is done, like the meme, and now is the turn of Gabriele. So let us check it what he has in mind for us.
Hi everyone and welcome to this video with Irrationalix. For starters, I'm very happy, I'm very honored to be here in the Irrationalix channel to solve with you, a problem, problems. So let's start with a problem about algebra. So, take a not prime number p, for example, and a field of all integers modulo p, and then we can construct a ring of polynomials over this field, okay? And we can take, for example, this polynomial q of x, and this polynomial has this form, okay? So I have some from key to from 1 to p minus 1 of this thing, and a key is equal to this key to pi minus 1 over 2 modulo p. Now, the problem asks to find the greatest non-negative number n such that x minus 1 to n divides q of x, okay? Perfect. So there are many ways to solve this problem. In this video I'm gonna to use a particular way that I consider very interesting. So for starters, we can define, so this is the problem, we can define now an operator d, and this is equal to x for derivative with respect to x, okay? So we have this. Now, and this operator is of this kind. Take a polynomial of this ring and get another polynomial of this of the same ring and of the same degree of the start polynomial. Why? Because here I have x2, okay? So the derivative of a polynomial lowers by 1 the degree of polynomial. If I had x, I leave the degree of polynomial unchanged, okay? So I have this. Perfect. Now, I can apply this derivative m times over q, and I can find this expression. We have this, okay? So why this expression? Because when I apply m times the derivative over q, I obtain many terms. Okay, every term has this factor x minus 1 to n minus m plus 1. With respect to this term hasn't this factor. Okay, and so when I study what happens for x equal to 1, so I have, sorry, here I have r of x for r of x, okay, modulo x minus 1. Rx is equal to q of x over x minus 1 to n, okay, where now m is equal to 0, 1 until n, and n is more small or equal to degree of polynomial q, and this is p minus 1, okay. Now, so when I apply the derivative m times on q, I obtain many terms, and when I study what happens for x equal to 1, I have that every term with this factor is equal to 0, and so I have just this term. So this is a pretty way to this expression is a pretty way to say this thing. Okay, perfect. Now I have that, for example, so I have this, remember these three expressions, okay, and now I have that if I apply the derivative d over q, I obtain two terms, a plus b, by the product rule, okay? These two terms, the first term is, for example, I have n for x minus 1 to n minus 1, okay? And this is a derivative, okay? Of course, here then I have r of x, here I have x minus 1 to n, but the thing in this term that change is just this, okay? And for x minus 1 to n minus 1, and here I have the derivative. So if I continue derivative this polynomial m times m minus 1 and other times, I evaluate this derivative at point 1, I obtained that derivative, I have that, of course, m is more small or equal to n. If m is equal to n, I have a pretty thing. In fact, I have that derivative n times, attention, so m is equal to n of q evaluated at point 1 isn't equal to 0. And so now I have that isn't equal to 0. Why? Because I have these two terms, okay? When I derive more m times, more than m times, I have here I have a thing that doesn't vanish. Here, this thing evaluated at point 1, this thing vanishes, okay? So this is equal to 0, and this isn't equal to 0. So derivative, so I have this expression. This expression is very important. Now, we can observe an important thing. What? We have that q is already a result of a derivative okay, of a derivative of over another polynomial. In fact, I have this. okay, s of x, where now this thing can be shown, of course. Now s of x is a power of x minus 1. In fact, I have x minus 1 to p minus 1. Now we can apply the same logic that I applied here to this case now. In fact, I have the derivative and times derivative pi b minus 1 over 2 so isn't equal to 0. Okay, I have this, and now I have that here. I have that n, okay, is smallest or equal to pi minus to p minus 1, that is the degree of q. Okay, and so if n is equal to p minus 1, I have this important thing. So this means that the degree of s is equal to p minus 1. Okay, and so I have that if this expression is right, n plus p minus 1 over 2 is must be equal to p minus 1, the degree of polynomial s. And so I have n plus p minus 1 over 2 is equal to p minus 1. And so the answer is n p minus 1 over 2. This is the answer. And it's a difficult problem, I think, but it's very funny to solve it. It's very funny to solve these kinds of problems. I'm very happy to be here in this channel, this amazing channel. So bye bye.
Okay, thank you very much, Gabriele, for your beautiful solution. And this video ends here. Maybe we will see again in English sometimes in the future. And well, there is nothing more to say, so goodbye.